Hi, class. So what we're going to look at now is the Vesper theory. And so what Vesper theory just means is that we're going to try to spread the atoms out as far as possible. All right, so as we're looking at this, if you look down at the four regions, so down here we have four regions of electron density, and we really assume that electron density is anything around the atom. All right, so it can be an atom because the atom is going to have some electron density. It can be a lone pair. It can be a combination of the two where you have some atoms, some lone pairs. As long as you have something with electron density, and an atom will have electron density, even as simple as hydrogen, we're just going to try to spread these out as far as possible. Right? So that's really what Vesper is trying to tell us, is that when we have atoms surrounded by regions of electron density, so we can do this for each central atom, that we're going to spread those groups as far as possible. Right? And the thought is that electrons have a negative charge. That negative charge, right? Just like if you try to put two magnets together that have the same charge, they'll repel each other. Same thing here. So that electron charge is going to try to push away from each other. One of the things we probably haven't talked about much is if you see this dashed line, that means it's going away from you. Wedge means it's coming towards you. And so the four things, it might be easy to think that, well, it should just be 90 degrees, right? Well, that would be if it was completely flat. If we do three dimensionals where the hydrogen is coming out towards you, so out of the plane of the paper, and the dash is going back, then you can get that extra space, and that's why you get 109.5. Okay? So all of these have that electron geometry of 109.5. Same thing when you have three groups. So now we don't care that it's a double bond for this exercise. We just care that there's three things, right? So if we're looking at the carbon on the left, there's 1, 2, 3. And the furthest we can spread things out is 120. Now, once you get to three things or two, it's going to be flat. So we don't have that third dimension. And so the furthest we can do is 120. So we're spreading those out. Two groups, you're going to be linear. And so you're just going to put one on either side. And so they're going to be 180 degrees. And again, doesn't matter if it's two double bonds, a single bond, and a triple bond. Even over here for the nitrogen, right? Triple bond on one side, lone pair on the other. Still two groups coming off of that atom. The furthest you can separate them is 180, so they'll be linear. All right, so one term that I would commit to memory is this tetrahedral. All right, so we've already talked a little bit about this. The carbons in a chain are tetrahedral if they're single bonds. So the geometry around this carbon is going to be tetrahedral. If it's three things, it's going to be trigonal planar. And if it's two things, it's linear. Now, this is going to lead in well because as we think about the shape, what we can talk about is the polarity. So we talked a little bit ago in one of our previous lectures that if we have something like HCl, right, that the more electronegative atom, so in this case, the chlorine, is going to steal the electron density. So what we would actually see is that we could put our arrow and it tells us that the electrons are going to sit closer to the chlorine and the hydrogen is going to lose its electrons, right? And so the electron density always goes to the more electronegative atom, right? So whichever one's more electronegative is going to pull that electron. So this is a perfect example of a polar covalent bond. So the electrons are still shared, just not shared evenly, right? So there's more electrons near the chlorine. Now, what we have to do is when we're determining if a molecule is polar, not only do we need to see if it has polar bonds, right? So what we've just done is identify that this has a polar bond. Right? The second thing we have to do is see what are these arrangement of these polar bonds in space, right? So are they all pointing the same direction? So if I was looking at HCl, yeah, I would say it's polar, right? It's got this net dipole, right? It's pulling the electrons in one direction. And all those arrows are going in one direction, right? There's only one, and so it's going in one direction. Let me show you a second example. If you look here at the bottom, we'll take carbon dioxide, and it's actually linear. And what we see is that between the carbon and oxygen, the electrons are going to go towards the oxygen. It gets partial negative, and the same thing to the other bond. And the carbon's partial positive in the middle. Now, what's important about this is that if you notice the two arrows, they're going in the exact opposite direction, right? So they're going opposite each other. So they actually cancel out. And so while the molecule above is polar, this would be nonpolar. Right? And so if you get that dipole moments where they're canceling each other out, then it's going to make the molecule nonpolar. So it's kind of that idea like tug of war. If two people are really, really strong, it doesn't matter if they're equally strong, right? Because they're going to cancel each other out. And so generally to be polar, you have to have two things. One is you have to have some polar bonds, or you have to have electrons going in one direction. A little outside of the scope of what we're talking about right now, but another thing, if you're looking for things to be polar, if it has a charge, right? So ions typically are really polar because they have a formal charge. But right now we're kind of looking at covalent molecules, but just kind of you're tying that idea together. Anything with a formal charge is going to be very polar. And then this is how you look at organic molecules and tell if they're polar. All right, the last thing, and we won't calculate these dipole moments, and definitely if you see vectors, you could do this in your physics class, but we won't do it in here. Essentially, we're just going to look generally at this dipole moment, right? Something like this, where is the molecule pulling the electrons in one direction? And then what's kind of the net gain of those? Are they canceling each other out? Is there some general direction they're pointing in? And so if they're generally pointing in one direction, they're going to be polar. If they're canceling each other out, it's going to be nonpolar. All right, a couple of examples. So the one we just did, right, is carbon dioxide. So here's the same picture we just did. Carbon in the middle, oxygen, oxygen. This is doing exactly what we just did. It said the electron negativity is going to go to the left, going to go to the right. They completely cancel out. All right, doesn't mean that they have to point exactly opposite. They just have to generally go in different directions. So for example, if you look at BF3, so our boron's in the middle, and then our 3 fluorines. Same thing is happening, right? Do you see how they're all spreading out opposite each other? And so they're going to cancel each other out. Same thing with carbon tetrachloride. Very polar bonds, but they're all going in opposite directions, so they cancel each other out. And so this is just one thing to be careful about, that if the bond is really polar, it's going to make you think the molecule is polar. But if they go in opposite directions, they tend to cancel each other out. So the ones that tend to be the most polar have one general direction they're going in. All right. So if we have something like water, right, on this one, the oxygen is more electronegative, so it's going to go towards the oxygen. Same thing on this one. It's going to go towards the oxygen. And now, do you see how we're generally going in one direction, right? We're generally going up. And so if we can kind of get them moving in the same direction, it's going to make this molecule very polar. So water is actually a very polar molecule. And it's because now those arrows are pushing in the same direction. So we're getting everything moving in the same direction of polarity. And so it makes the molecule very polar. Switching gears a little bit, and we talked a little bit about this when we talked about electron configuration, but we're going to kind of circle back to it and think a little more deeply about it. So I drawn some small cartoons when we originally talked about this, but now this is a better picture to visualize it. Right? So our s orbital is just a sphere. Right? So our nucleus will be in the middle, and our electrons are somewhere in this electron cloud. Our p orbitals, if you remember, we talked about there being 3 of them. So px, py, pz. All look about the same. They look exactly the same, except they're just the axis they're sitting on. And they really look like these hourglasses, right? Does everyone see kind of these figure 8s and hourglasses? And they're just going along these different axes, whether it's the x, z, or y. And then the d orbitals are down here at the bottom, and they're a little more intricate. We won't talk about these in this class. The one thing I wanted to highlight about them is there are some elements that have them. So especially as you go further down the periodic table, we talked about the exception to the octet rule being sulfur, phosphorus. We won't talk into detail of how they work, but metals. A lot of the catalysts have a lot more flexibility in terms of the bonds and electrons they have, and it's because they have these d electrons. Right? So for us, we'll mainly focus on the S and P, so make sure you commit these to memory. But there are more orbitals, and so I just want to highlight that we're only looking at a small subset, but it just happens to be the ones that we see the most in this class. So carbon atoms, oxygen, nitrogen tend to only use S and P, and so that's why we're going to focus on those. And it looks like we're moving away from that, but we're actually talking about another topic, and then we'll tie the two together. So right now we're talking about covalent bonds. And so if you remember, we talked about covalent bonds being the sharing of electrons. And so one of the classic examples of a hydrogen bond is one of the simplest covalent bonds. Each one has one electron. So it brings the one electron to the middle, right? Remember the fish hook, right? Or this barbed arrow tells me that there's one electron, and they're going to come together. And we make a single bond between the two. All right, and so we stick them together. What this tells us is that by doing the process we just did, that by bonding molecular orbitals, so MOs, molecular orbitals, in which electrons have lower energy than they would have as the isolated atomic orbital. All that's saying is that this electron is sitting in some energy level. By pairing the two up, that energy level goes down. All right, so pretty straightforward, right? That they like to be paired up. Right, so when we bond them together in these orbitals, the energy level goes down, so it's favorable. Right, things happen if it happens to be a lower energy level. It tends to be spontaneous. One of the next things we're going to look at is electron density is concentrated between the two atoms. And here's nuclei, because that's all we can really see, and the electrons are over them. And they lay across a cylindrical symmetrical axis. And so what that means is that when they overlap, they're going to sit on top of each other, right? So you're going to have the two atoms, and the electron density is going to be right in between. And so that shows that those electrons are being paired up right in the middle. And so this, my Apple Pencil just becomes that electron density it's talking about. So you're going to have your two nuclei, and you can see the electron density concentrated in between them. And that's showing that the two electrons are coming together to make a bond. And I'll show you what the orbitals look like when they overlap. But that's all it's saying, is that when we put the two together, our nuclei is what we can see. So it's the center. And then my Apple Pencil would be that electron density sitting there. So, and we say density, and we'll talk about this when we do resonance structures, but it's a much more fluid. The electrons are moving. And I know it sounds kind of a little wishy-washy, but they are moving around as opposed to like a steel bar that locks it in place. And we'll see why this is important later when we draw different structures of the atoms. All right, so hopefully this next picture kind of puts it together. All right, so this is doing the same example we just talked about. So if we take a hydrogen, here's my hydrogen, my other hydrogen electron, they're both sitting in the 1s. Remember, that's the lowest energy level. And there's some energy level associated. So here on the left is telling you that as we go up, the energy level gets higher. What we want to do is pair these electrons up. So just like we did when we finished filling those energy diagrams, as we moved up, we'll put one electron down in the sigma bond, right? So sigma bond means single bond between the two. And we'll pair them up. So one electron goes down, second electron. And remember, the s orbital can hold two electrons. Now we've paired up those two electrons. And all that text on the previous slide was just trying to tell you that we start at some energy level, but pairing them up, they actually go down. Now, one of the terms you might have heard in Gen Chem is the excited state. So we can push an electron up into a higher energy level. It's an excited state, so it probably doesn't last. It's not favorable. And so this electron will stay up here for a little bit and then usually pops right back down. So we're not actually going to talk a lot about that right now because it's something that we'll look at later when we talk about like light being emitted, right? Or harnessing that energy. But when we're talking about just making bonds, we want to see this ground state here on the left, right? We're pushing one electron in, putting a second electron, and they pair up, right? And they want to stay in this lowest energy level. One more thing, and then we'll kind of put this all together. All right, so hybridization just means that we're going to take all the orbitals and kind of smash them together. All right, and so hybrid orbitals just means we're going to take the number of hybrid orbitals formed is equal to the number of atomic orbitals. And what that's telling you is if we look at the picture down here at the bottom, we have a 2s orbital. So there's an s, and then there's 3 p orbitals. So altogether, we have 4 orbitals, right? An s and 3 p's. So when we hybridize them, we should have 4 orbitals as well, right? We had 1, 2, 3, 4. So now we have to have 1, 2, 3, 4. Okay? Now, where this comes from is that the S should be a sphere, the P should be this hourglass, but in reality, they don't actually look like that. They all look the same, right? And when they all look the same in these atoms, right? So in methane, for example, is something that looks like this. If it was true that one of them was an S and the other 3 were P's, one of these bonds would be really short, right? Because it's kind of that sphere, so it'd be sitting close to it. And the hourglass shape of the p orbital is a lot longer, so the other 3 would be longer. But that's not actually what it looks like. All 3 bonds are exactly the same. So what happens is we actually smash the 2 together, right? And we make these hybrid orbitals. Now, the 3 types of hybrid orbitals you'll see, and I'll explain the differences as we go through, we'll work through them systematically. But one thing I would commit to memory is you're going to have these 3 different hybrid orbitals. All right, so it's sp3, sp2, and sp. It literally defines what it's made of. All right, so if you're looking at this, let's start with sp3. It tells you that this hybridized orbital is made of an s orbital and 3 p's, right? Exactly what happened here. There's an s and then 3 p orbitals. And so that's what it's made of. If it's sp2, then it's made of an s orbital and then 2 p orbitals. If it's sp, it's just made of 1 s and 1 p orbital smashed together. All right, so it literally tells you what it's made of. Now, the way this is going to work is you almost want to think that you're going to take all of these orbitals you have to play with, put them in a blender, smash them up, and they're going to look exactly the same. All right, so if we're looking at this one and we want to see what it looks like, it's actually exactly the composition of this. Okay? It's going to be 1/4 s, 3/4 p. And it'll be these p orbitals divided up evenly, right? So if there's 3 p orbitals, we would essentially divide these up into 4s and put in each one of these. All right. And so this is going to be an even makeup of the p orbitals in s. You see the energy level? It's going to be split between the 2, and it's not split right down the middle because there's 3 p orbitals contributing to the energy versus just 1 s. So that's why it's a little bit higher, right? Because the p orbitals are higher in energy, so it moves up a little bit because there's a greater contribution from the p orbitals. Now, last thing about this is since all these orbitals are exactly the same, right? They're all sp3. Then if we think back to our electron configuration rules, remember of how we fill up these energy diagrams? When the s was lower, it made sense to fill it up first and then start adding them to the 2p. When they're hybridized, we add 1 in each level and then go back and start pairing them up. And the reason we have to do that is now they're all at the same energy level. So our rule tells us that we put 1 in each of them before we go back and start pairing them up. Yeah. All right, so this is the example we were just talking about with methane. All right, so let me redraw the structure on this page. So if we had our carbon atom, hydrogen, hydrogen, and another hydrogen, we'd have our 4 bonds, our carbon in the middle, our 4 hydrogens. And now what happens is the carbon is going to sit right in the middle. Let me draw it right here. So my carbon is sitting in the middle, and then my hydrogens would be sitting on the outside. And so the way this is going to work is my orbital, and let me put it in a different color, maybe green. If my hydrogen is out here, hydrogen only has the s orbital, And then there's the overlap that we talk about. Same thing over here. There's the overlap. And we kind of get the same for each one of these. And so those hybridized orbitals are what makes the bonds to the next atom, whether it's a hydrogen or a carbon, but we're going to make the orbitals overlap between the two different atoms, right? So regardless of what they are, so in this case, it's hydrogen, there'll be some overlap. And this is how we know that there's this hybridization, is that all four of those bonds look exactly the same. Now, when we hybridize orbitals, we can hybridize atoms just like we did. And so we're going to actually, not the atoms themselves, but the bonds coming off of those atoms. So if you look at the first one, it's exactly what we just did. We took our methanes or our carbon, our hydrogens. So the hydrogens will only have an s orbital, and they can't hybridize. And it's because they don't have any p orbitals, right? They only have an s. So they're always just going to be a sphere. And then here's my hybridized sp3 orbital. Hybridized sp3 orbital and the hydrogen over it. Right? And let me put the hydrogen one in a different color because I feel like it's a little hard to see. So there's my hydrogens, and they're overlapping. Right? And so the overlap between the two is between the sp3 of the carbon and the 1s of the hydrogen. Right? So there's our sigma bond, right? And our sigma bond is our single bond. So we have our sigma bond created between those overlaps. Now, we can do bonds, right, between hydrogens and any atom. So it doesn't matter that it's a nitrogen. Right? So we'll do the same thing. The other thing we can do is lone pairs will sit in those hybridized orbitals. So if we're looking at this nitrogen, it's still sp3 because it's hybridized with 4 different groups, right? So one of these sp3 orbitals is still sitting where that lone pair is, right? So the lone pair is sitting in one of those sp3 orbitals. And then if we look at the hydrogens, it's an s orbital overlapping with an sp3. Same thing on the right, sp3 overlapped with an 1s. Right? Same thing with oxygen, right? So if we have water, it's half and half now. So it still has the 4 sp3 bonds, right? Or those sp3 hybridized orbitals. And they can make 2 bonds, one to a hydrogen, one to another hydrogen, and then the 2 lone pairs can sit in there. Right? So we just want to think about what orbitals are making that bond. Right? And so if it has 4 groups, it's going to be sp3, and then hydrogen will always be 1s. Now, sometimes when we have a double bond, we can only make double bonds from p orbitals. Right? So one of the tricks is we can only make double bonds from p orbitals. So what we're going to do is save one of this one. So we're going to save one of those p orbitals for the double bond, and we actually call those double bonds pi bonds. And so we're going to save it for that pi bond, right? Which means that now it's no longer there to be hybridized. Right? So the only ones we can hybridize are the ones that we leave behind. Right? So we're going to save this one for our pi bond. So we're going to keep one of the p orbitals. And now when we hybridize them, we use 2 p's and 1 s. So that's why the new name is sp2. And it literally describes what it's made of, right? There's an s orbital. So that's why there's an s. There's 2 p's. And that's why there's 2 p's. And if it helps, what I can do is highlight where those orbitals came from. And maybe this will help. Is that hopefully you can see that the sp2 is a mixture of the 2, right? So now they each have a little bit of the s orbital in them. They both have, all 3 of them have a little bit of the 2 p orbitals, and they're all mixed together, right? And then we completely saved that other orbital for the 2p. Right? So anytime we're going to have a double bond, we have to save one of those p orbitals, and so we can only hybridize the other atoms or the other orbitals. Same thing. Our atom's going to be in the center. So if this was a carbon, our carbon would be right in the middle. And now you can see the orbitals. And so what we actually have is a little bit different shape. It's still figure 8, but that non-bonding on the opposite side is actually a little bit smaller. Okay? And we're going to have 3 of them. And so when you see your 2 orbitals, they're actually going to sit on either side. And we can start to overlap the atoms. Okay? So if we did the same thing, if we made this with a hydrogen, so if we had another atom come by, let's say it was hydrogen, it'd be an s orbital, and they would just sit right on top of each other. And so we're doing the exact same thing where they're starting to overlap, but now they're sp2 instead of sp3. Sorry, one last thing before we move on. So if you're trying to figure out, so we've used the 3 hybridized orbitals, but where's the p orbital? The p orbital is going to sit perpendicular to the other ones. So here's my p orbital that we didn't use. I'll sit right here. And so typically what we'll do is we'll use that for a double bond. So I can show you here in a second, but it's going to sit perpendicular to the rest of the 3 that are sitting flat. All right, let's try one more and then we'll tie it all together. So now, if you have something that makes a triple bond, so we're going to have our triple bond, we have to actually save 2 p orbitals. All right, so we're going to put 2 of the p's away, which means we kept 2 of these. And so now, when we make our hybridized orbital, we only have an s and a p. So this will be half s, half p. And so that's why it's sp, because it's literally made up of an s orbital and a p orbital coming together. And it's because we save these other p orbitals to make our pi bonds, right? So we're going to save those for the triple bond. Let me show you what that looks like. All right, so as we're looking at this, let's talk about how these orbitals overlap, and we'll kind of build through all of them. So we have this molecule here on the left, so ethane, carbon, hydrogen, carbon, and some more hydrogens. I think we've already talked about that a line means that it's bonded, right? It's sharing those 2 electrons. But what this chapter is trying to get at is, how are those electrons actually interacting? Right? And so our sigma bond is our single bond. Right? So we're going to create a single bond between carbon and hydrogen. And so the sigma bond is going to link the 2 together. And we're going to see that sigma bond right here. And we just want to think about the hybridization. So if we're looking at this carbon, we're going to count the number of groups it's attached to. 1, 2, 3, 4. And so if it's attached to 4 groups, it's going to be sp3. Hydrogens will always just be an S. And if you want to be specific, it's always going to be the 1s. Right? So if it's attached to a double bond, then it's sp2. And if it's a triple bond, it's sp. So the best way to think about it is if you have 4 atoms, or lone pairs, you're going to be sp3. If it's 3 atoms, I'm going to put and because it can be any combination. Then it's going to be sp2. And if it's two atoms or lone pairs, then it's sp. Right. So the reason this is going to be important is if we come over here and look at our carbon, this carbon is going to be sp3. The hydrogen is S. So if we're going to describe that bond that links them, we're going to say it's an overlap of a sigma bond between an S and an sp3. Now, if we're looking at the carbon bond, we want to see what the hybridization is of this carbon. It's sp3. The hybridization of this carbon is sp3. So that's why the bond right in the middle is a carbon-carbon sigma bond that overlaps two sp3 orbitals. Right? So when you're talking about what bond it is, you just want to find the hybridization of each atom that's making that bond. And that's going to be the type of bond you have. Over here, it's telling you that we have sp3 with hydrogens, which are the 1s. And so each one of these bonds here, and actually all 6 of these, is a carbon-hydrogen sigma bond that's made from the overlap of an sp3 and a 1s orbital. We'll practice some more of these and we'll keep getting good at it. All right, same thing here. All right. We can use our cheat sheet that we just did on the previous side. If we're looking at this carbon, it's attached to 3 things. So 1 atom, 2, 3. We don't count the bonds, we count atoms or lone pairs. So if we're attached to 3 things, we're sp, I got ahead of myself, sp2. So that means if we look at these orbitals, all the carbon and hydrogen, remember hydrogen is always 1s. So it's going to be the carbon sp2 and the hydrogen 1s. Right? And that's the orbital overlaps that are between the carbons and hydrogens. Right? Now, if we look at the sigma bond, right? So it's the single bond between the 2 carbons. So it's just that first bond between the carbon and carbon. They're both sp2. So that means the overlap of them is between 2 sp2 orbitals. Right? And that's because both carbons are sp2. All right, now the other thing you're going to see is we kind of have these gray spheres. Does everyone see? You have a carbon-hydrogen bond, carbon-hydrogen, carbon-carbon, hydrogen, hydrogen. The ones we haven't used are these p orbitals. Right? And so remember, there's a double bond, and that double bond comes from a pi bond. And the difference with a pi bond is, see how these orbitals are colored differently? So there's the pink one, they're going to make an interaction, and the bottom one's going to make an interaction. All right, and these two kind of smear more together. And so when we're talking about that MO theory, we talked about that cylindrical down a symmetrical axis. It literally just said, it's kind of the way you would think about nailing 2 boards together. You're going to put the boards on top of each other and then like stick them together. That's kind of what we think of bonds, right? They're literally going to be glued on top of each other. This one is more like they're perpendicular like goalposts, and then you start to smear that electron density between the 2, and they make that double bond. And even though it looks like maybe there's 2 different bonds, it just makes that same interaction on top and bottom of that orbital. And so together, these make that pi bond, right? So there's that interaction on top and on bottom of those p orbitals, right? Remember, we can only do double bonds with p orbitals, and it's because we need that kind of hourglass goalpost shape, right? Where they're pointing straight up and down and they can interact with each other. So these blue lines here actually are what's representing your pi bond, right? So it's those interaction between those p orbitals that makes your pi bond. Triple bond's the same thing, and so there's a picture over on the right of the molecule we're going to look at, right? So we're going to look at hydrogen, carbon, triple bond, hydrogen. Now, if you're looking at this, the carbon is attached to two things, so it's going to be sp. This carbon is sp, and then don't forget our hydrogens are always 1s. Now, let's just kind of draw this from scratch, because I think if we look at the first picture, there seems to be a lot going on. So if we have our carbon, 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 and before I put my double bond and triple bond, let's just draw the orbitals. So if we have our hybrid orbitals, it's going to be an sp, and so you're going to have an sp that overlaps like this, and an sp from the other carbon that overlaps. Right? And we start to get kind of this interaction between the two, and that makes that sigma bond. All right. And so that first bond that we've drawn is the one over here on the right. Right? It's a carbon-carbon sigma bond, and it's an overlap of those two sp orbitals. Right? So both of these are my sp orbitals that are overlapping on top of each other. All right? Don't forget, if we have sp, that means we have two of them. So there's a second one pointing towards the hydrogens. All right? So those will also be sp. Now, hydrogen is always just the s. So those are my s orbitals. And so those hydrogen bonds is the overlap of the carbon sp and the hydrogen s orbital, right, on that outside. So this is the overlap of an s and an sp orbital overlapping on the outside. All right, now what happens is we're going to have a p orbital and a p orbital. And just like on the previous picture, let's get the gray, we're going to get a nice overlap on top and a nice overlap on the bottom. And so that's going to make one of my pi bonds. All right, if you look over here, we actually have done that twice, right? We have one here. And then let me find a different color that kind of stands out. Maybe a green is going to work. And then we have a second one that kind of stands out this way. And those are my two P's. So then we'd have a second one. And they're going to interact right here and here. And so remember, you get that top and bottom interaction. So I know there's a lot going on. Maybe we can just take a step back. So the first bond you ever make between two atoms is a sigma bond. Right? So the carbon-carbon sigma bond, carbon-hydrogen sigma bond, and then on the other side, carbon-hydrogen sigma bond. Each additional bond after that first one is a pi bond. So this is going to have a pi bond on the top and a pi bottom on the bottom. Okay. Remember, pi bonds are only ever made by p orbitals, so they're going to have that hourglass shape, right, or that figure 8. And then if you ever ask what's the orbital, right, that are used to make a bond, you just find the hybridization of the atom and the hybridization of the atom that's bound to. Right? If it's hydrogen, then it's always s because it can't hybridize. Last thing, and this last slide kind of boils everything down to maybe a little more simplistic view of everything. If you're looking at this picture, okay, if you're bonded to 4 groups, you're going to be sp3. Okay? And so the reason we use the term groups is because remember, groups can be atoms or lone pairs. All right, we're just going to count them up. All right. The atom is going to be sp3. Right? So if we're talking about the orbitals, if it has 4 groups, it's going to be sp3. And the general bond angles are going to be 109.5. Sometimes you have lone pairs and stuff, it kind of squishes them down. And I think maybe in Gen Chem, you spent a little more time that like ammonia is like NH3 with the lone pairs, maybe like 107, and water's like it squeeze them down. For us, 109.5 is fine. And then if it's a carbon with 4 groups, all of those are going to be sigma bonds. Now, if you have something with 3 groups, right, you're going to be sp2. And so this is what I would commit to memory, is this idea that 4 groups make you sp3, 3 groups make you sp2, 2 groups make you sp. And remember, you're not counting bonds, you're counting atoms or lone pairs. Same thing if you're sp, 180, and so we're exactly opposite each other. Right? And those other 2 p orbitals that we didn't use go to make a pi bond. All right, so let's try one real quick. So I'm going to draw a small molecule. All right, so what I would do is pause the video and go through and label each of the atoms as sp3, sp2, or sp. And you don't have to do the hydrogens because they're all s. Right, so everything other than hydrogens, label them as sp3, sp2, or sp. All right, so pause the video and give it a try. All right, let's try this together. So if you're looking at the first carbon, it's attached to 1, 2, 3, 4 things. Right, so if you're attached to 4 groups, you're going to be sp3. If you're looking at the next carbon, remember, we're not looking at bonds, we're looking at atoms or lone pairs. It's 1, 2, 3. So if it's only 3, you draw a long arrow just to kind of keep things a little less messy. So sp2. Now, I think this is actually one of the tougher ones. We have an oxygen on top. It's got 1 lone pair, 2, 3. So again, this one, sp2. Right? Lone pairs, we're not counting the individual dots. We're counting them as a pair. So it has 3 things. So it's sp2. All right, the carbon here is going to be sp3. Now, same thing as the oxygen. If we're looking at the chlorine, it's attached to a carbon, a lone pair, lone pair, lone pair. So if we count each of these up, it's 1, 2, 3, 4. So if we have 4 groups, you're sp3. All right, one last thing. Try to figure out what would be the bond, the orbitals that make that bond. All right, so go ahead and pause the video, give it a try based on the examples we did, and then I'll do it for you here in a second. All right, so if we're looking at this green bond, the way we would solve this problem is we're going to look at the 2 atoms that are attached to it. So in this case, it's the carbon and the other carbon. All right, one of them is sp3 and the other one is sp2. So if we're asked to describe that bond, it's a carbon-carbon sigma bond, right? Because it's a single bond. So that's why it's a sigma bond. And then it's an overlap of an sp3 and an sp2 hybridized orbitals. Right? So the way you would do that is just by looking at the hybridization of the atoms. All right, we could do the same thing even for oxygen. So if we're asked to describe the sigma bond between these 2, it's an oxygen sp2 bond with a carbon sp2 bond. And so it would just be a oxygen carbon sp2 sigma bond. All right, so we're just going to find the hybridization of that atom and link the 2 together. Hydrogen's always s. And then if it's a double bond or triple bond, they're always made with pi bonds, right? And they always come from the p orbital. All right, so that pi bond or double bond is always made from the pi bond. All right, I hope this was helpful.